Just a second. Okay, now you can see me probably. Hello, everybody. Good morning. My name is Jelena Kovačević-Dojčinović, and I will be chair for this session. This is Extragalactic morning session, and we have 6 speakers for this session. The first one is Professor Dr. Dragana Ilić. She is from Faculty of Mathematics, University of Belgrade, and the title of her talk is Quasars Research in Time Domain Era. Dragana, you may start your lecture.
Thank you, Jelena, and I thank all the organizers for making this a very important event for the Serbian astronomy happen. And I am really proud to be the opening speaker of this extragalactic session. I have to say that it is a great privilege for me to give a first invited talk. And I also want to emphasize and to thank especially to Angelika and Jelena, the chairs of this, the co-chairs of this conference, for facing all the challenges with the COVID-19 pandemic and all the new way of how the science is being done, and especially how conferences are being organized. And I found very important that we all together, especially you, managed to make this conference happen. So thank you very much, and thank you all Scientific Organizing Committee for this opportunity to give this talk. So I'm going to present the talk. I'm going to present the research which is currently being not currently, but in the last many years being conducted by the group of the group in Belgrade. I just want to, I don't know whether you hear me well. I guess you do.
Yes,
otherwise you would say
just
okay.
Continue.
Okay. So I will keep my video as long as the connection is stable. So I'm going to talk about quasar research in time domain era in Serbia by the Serbian group, and I listed here only the 3 key persons who are kind of driving force in the last time, and this is apart from me, Angelika Kovačević and Luka Popović. So this is both efforts from the people from the University of Belgrade, from the Faculty of Mathematics, Department of Astronomy, and Astronomical Observatory of Belgrade. And I'm talking here about quasars, but actually these are all active galactic nuclei. I'm just using the word quasars in order to have a shorter word. So to begin with, I'm just going to start with several introductory slides. Quasars or active galactic nuclei are the most very bright objects and very distant objects. And here I'm just showing an example of one of the latest quasars found, and one of the most distant quasars known, which began to shine just shortly after the Big Bang. And this is just a little point that you see in the middle of the screen. So why I just want to show you this is that basically what we see about galaxies and most of the quasars is just points. So we don't really know what's happening there when we just get the images. Maybe from the colors we can get some more information, but how we actually can, and my talk here is going to be how we actually can zoom in these little points with time domain investigation and find a lot of interesting physics going on. So what are quasars and what are AGNs, or active galactic nuclei? Basically from all these points, what we receive really various observational properties. So most important, they are of high luminosity, and they emit on all possible wavelengths. So from gamma rays to radio bands. And so the spectral the spectral energy distribution from these objects is very peculiar, and that's what makes them special apart from being just points. and they emit very strong, broad, and narrow emission lines. This is what we see in optical spectra, and I emphasize this because our previous research was focused on spectral optical investigation. And then there's another feature from these objects, and this is that they're strongly variable, and this is what makes them perfect cases from time domain analysis. And therefore, for all these different observational properties, we have many different types and subtypes of AGN. So from Seyfert galaxies, radio galaxies, quasars, and so on, and many different subtypes. So, and all these subtypes are unified in one model, which is saying that in the center we have the supermassive black hole, and we have a accretion disk of gas going into the supermassive black hole, and that the main power source, which is responsible for all this enormous energy emitted from the core of a galaxy, is the accretion of matter into the supermassive black hole. And when we say supermassive black holes, this is from like tens of millions and to tens of billions of solar masses. And we will have a very, probably very exciting talk in the next session about supermassive black holes. Apart from the accretion disk and around the supermassive black holes, we have a number of clouds emitting broad, which are lines which are very close, following basically the accretion disk geometry. And then we have also the narrow line region, and we have these dusty regions surrounding all this area. So very complex geometry and a lot of interesting physics going on there, and it's just not as easy as it's shown on this sketch. What is other important thing to note is that we make two different types of AGN. So we distinguish between type 1 and type 2. And this is illustrated in this sketch, basically depending on the way how we observe these objects, how they are oriented towards the observer. We may observe the type 1 AGN. So we basically observe within this obscuring regions, and we see basically the broad line clouds, and this is why we see the broad lines in the spectrum. These are the type 1 objects. And then there are these type 2 objects, which we observe from the side somehow. So basically there are the obscuring regions which block the central area. So we don't see these broad line clouds, and we see these only narrow emission lines. So all these basically regions are of line emitting regions are closely connected with the continuum emission regions, which is coming from the accretion disk, and all together is basically connected because the continuum emission from the accretion disk is ionizing all this gas around. So starting from the broad line region, narrow line region, is also transferring heat to this obscuring material. So another important feature of quasars, apart from these broad and narrow emission lines, is that which we see in the optical spectrum. So these are the optical band spectrum, and our focus in this research is in the optical band. Is that the spectral variability of quasars in every band, but especially also in the optical band. And this is a good feature because everything varies. So the line flux, the continuum flux, even the line profiles are changing. You can see here an example. Let's see an extreme change of line profiles. So in one epoch, you see very broad H beta line, and in the next epoch this line is gone. So these are a type of extreme change of AGN. So sometimes they even change this type from type 1, which is the broad lines, to type 2 without broad lines. And these are the so-called changing look AGN. And there has been a lot of exciting research in our group on these objects lately. So how can we use this optical variability of quasar? And this is something to introduce this aspect of time domain astronomy, which is of course was always present because especially the objects in solar system were variable in the sense that they were changing their position and the, the brightness. But this concept of time domain astronomy is now how the astronomical is more referred to the astronomical variable astronomical objects beyond the solar system. So the active galactic nuclei and quasars and blazars, which are very also very dramatically varying, are great examples of these objects for time domain astronomy. Of course, supernovas and transients are as well an important examples. And why this time domain astronomy is becoming very important now, because we have very large time domain surveys, so which are constantly monitoring different the whole sky. And this is the, for example, currently active Zwicky transient facility ZF, and all getting prepared for the next coming survey, the of the Vera Rubin Observatory. This is the large survey in space time, the so-called LSST. And I put here a small commercial, and this is a logo of a project which is just being formulated. This is the Extra Universe project, which has been submitted to the Serbian Science. It's a proposal for a future investigation of our group and for the within the call of ideas. So I just want to come back a little bit on the broadline region, because we have been studying the broadline region in the last time a lot for the in this time domain aspect. So the broadline are present in those sort of type 1 AGN, so those which are non-obscured. So there is a mistake here. How do we actually, if I bring you back to the first slide, so we see only points, and it's very difficult to resolve the inner part of AGN. So how do we know there is a broadline region? But basically, we do not know. I mean, we see it from the spectrum. You see here, I mean, SDSS spectrum of a quasar, and you see that there are broad lines. So therefore, there is a region which emits these broad lines, and this we call the broadline region. So far, this region, this is a beautiful some sort of sketch, but we have not basically seen directly these regions, only with special instruments such as the gravity at the VLT, basically using interferometry, we could resolve in some on some wavelengths, and basically in the near infrared this area, and basically see the broadline region in Paschen lines. So spectroscopy is very important, and there are still many open questions about this broadline region, because we cannot really resolve it and study their properties. For example, some of the fundamental questions of what is the gas temperature and what is the density in this region, it's still a sort of a driving question for this investigation. And what is the kinematics? Do we have outflows, inflows over there, or what is basically the geometry? Is it following the accretion disk, or we have radial motions and so on? And so many open questions. So basically, a lot of groups are investigating this area, but some of the hot topics why we want to study the variability of broad lines and the variability of in the optical of quasars are listed here. So most as I noted before, is that these core and the broadline region is not possible to be directly imaged, but we can resolve it in time domain. And this is which I will be explaining in several minutes. So we can basically study the accretion disk and the broadline region to the techniques which is called the reverberation mapping. And through this technique, which I will explain in the next slide, we can basically directly measure the unseen. We can measure the size of the broadline region and use this to estimate the mass of the supermassive black hole. And this is something which is a very an important feature and important result from the studies of active galactic nuclei and on the broadline region, is that we can, from the variability of the broad lines, estimate the mass of the supermassive black hole. So the reverberation mapping is one of the priorities of several future surveys. One of it is the LSST, and also the Mauna Kea spectroscopic explorer, which I will mention later on. So another feature is to detect oscillation in AGN light curves. We can search for periodicities, and these are important because we can get possible gravitational wave sources. And of course, from the variability, you can get these extreme cases of variability, this sort of changing look AGN, which is a puzzle for all research. So reverberation mapping is basically explained here. If we have the emission from accretion disk, the continuum emission, you see the light curve of the continuum here. And you have the emission from the broadline clouds, and you see the light curve here. These emissions are delayed one to each other, because if there is a change in the accretion disk, the continuum emission needs some time to reach the clouds and provoke this basically change which is seen in the accretion disk. And this time delay is basically because light needs some time to cross it, is equal to the size of the broadline range. And we can use, if the gas is virialized, we can use this feature, the size and the velocity of the clouds to get the mass of the supermassive black hole. And this has given this famous radius luminosity relation, which can be used to get the supermassive black hole observation from basically single epoch observation. And you just use this, you get the luminosity of an object and you get the size from the relation, and by estimating the velocities from spectra, you get the mass. So this has been vastly used, and this is why we, in the last decades, have been running a very long-term monitoring campaign with our dear colleague Alla Shapovalova, who unfortunately passed away last year. Alla has been a PI of this campaign for decades, and he has get together several important telescopes in Russia and Mexico and Spain, and we are continuing her legacy and adding new telescopes to the monitoring campaign. So from Rožen, Asiago, and as well in the southern Serbia in Vidojevice. And last night I tried to observe these objects. So if I'm a bit tired, this is why. Unfortunately, we didn't have really good weather, but we did some tests. So these are just some of the results of our long-term campaign, some of the light curves and estimated lags and masses of the supermassive black hole. And these observations, of course, have, I just want to emphasize that in our sample of objects, we have different type 1 AGN. So with different subtypes, different variability, and with different spectral behavior. So this makes it a sort of a unique. Apart from that, we have a really 10 plus years of data. And one of the important features is to emphasize that the results of our campaign were included in the AGN black hole mass database of the group in the Georgia University. So another results which has been recently released basically this year is the investigation of one of the smallest supermassive black hole in AGN, and this is in NGC 4395. This is only 10,000 solar mass black hole studied by the group of Young-Hak Vo in Korea. and this result has been published in Nature Astronomy last year, and they conducted basically an extended and international monitoring campaign, which included as well the Vidojevica telescope, a 1.4 meter telescope, and these investigation showed that the time delays were only of an hour, giving this very small supermassive black hole. And if you see this radius luminosity relation, this object is really in the low luminosity end, and it shows that it basically is following the radius luminosity investigation. So, which is a good result for the Vidojevica telescope. These were one of the first observations performed on Milankovitch telescope. So another important feature from these investigations are the hunts for supermassive black hole, and these are basically the way how to extract from long-term light curves periodic oscillatory behaviors, and this is something that has been lately developed by Anđelka Kovačević, a very novel tool how using the value transformation and correlation coefficients on Gaussian process light curves to extract oscillation and get the periodicities. Another challenge from these variability studies is to study these extreme changing look AGN, which basically have this appearance and disappearance of broad lines within just few years. And these are very good cases to study the evolution of AGN. So basically what causes this change? Is it variable accretion disk or some obscuration or tidal disruption event, or a binary black hole system, which has been shown by Eddie Bon and Wang in their latest publication. So this is very an important case, and this is one example which was discovered in our long-term data. So NGC 3516 is shown that it changes in these 20 years. The type basically in 2014, the broad line is completely gone. And recent observation in the end of last year shows that maybe this object now is starting to awake. So it is really important to monitor, continue monitoring of this object and see, try to catch this object in the awakening phase. So just to come to the most sort of future perspective of our investigation is basically oriented towards two important missions, and this is the LSST, the Legacy Survey of Space and Time of the Vera Rubin Observatory, which is just going as we speak. So it's planned to start to observe in 2023. It's an 8-meter telescope in Chile, which will give big data, a big movie of the sky. And another one is the Mauna Kea Spectroscopic Explorer, which is 11.25 meter telescope, 11 meter telescope located in Hawaii, which is planned to start in 10 years or so, and we will do massive spectroscopy, basically a multi-object spectroscopy of 4,000 objects at once. So we have already started to collaborate and to be part of the LSST. And this September, there was a call for proposals for in-kind contribution of international teams. And the Serbian AGN team, the so-called SERSAG, contributed with a proposal, and we basically suggested two in-kind efforts. One is the directable software effort for the analysis of variability of celestial sources, and the other one is the optical follow-up bright LSST transients using the Milankovitch telescope, which will be done through the ION network. And this is just the real image of the LSST to show that the telescope is almost, I mean, the dome and everything is almost finished. And this is from April 2020. So the LSST is really happening. And this is just an example of the works that we have been doing for the LSST. Is the estimate of the necessary cadence for the LSST. So we proposed a metric using our own variability, our own light curves and the properties of our light curves, such as the variability level, the redshift, the luminosity, to estimate the cadence of necessary for our studies. The another important future survey is the Mauna Kea Spectroscopic Explorer, and so this will be mounted on the on a Canadian, Hawaiian, French telescope, which is already basically the dome is already existing on Mauna Kea, and it's basically a recycling of a dome because they will use the same mount and put the new telescope, which is larger than 11 meters. So this is a very peculiar feature, and Luca and I are currently working as members of the science collaboration to define what are the spectrograph performance which are needed. And so one of the key science cases for Mauna Kea Spectroscopic Explorer is the reverberation mapping, and it will do the most basically of the will do the robust estimates of time lags for the largest sample of quasars. And of course, because it will have a very good spectrograph, we will be able to do other science cases like with high resolution spectroscopy, like velocity resolved reverberation mapping, do the hunt for spectroscopically resolved binaries, and so on. So we have we have the LSST on one side and the Mauna Kea Spectroscopic Explorer, both massive time domain surveys. So for these, we really need to develop new tools and new methods how to extract data in an efficient way. And this is basically the preview and commercial for the next two talks. One is using the machine learning algorithm. So the Isidora will give talk in a few minutes. And the other one is how to develop some autonomous tools to analyze the AGN spectra, and this is the code Fantasy, which Nemanja and I have been working a lot on, and he will present this. Another important tool, which is part as well of our Extra Universe project, is the analysis of time series with machine learning algorithms. And this is the code developed by Anđelka Kovačević. So this is based on Gaussian processes, and she's working on this Gaussian processes for time delay estimate code, and specifically in spectral campaigns, but this is happening in any sort of time domain analysis. Light curves, especially long-term light curves, can have a lot of problems like gaps, non-uniform cadence, rolling cadence, and so on. And so if you have such a light curve, it's really important to get a reliable modeled light curve, and the Gaussian processes have shown to be a very good way. So you can read a lot about it in Anđelka's papers. And one of the next as well important tool to get the new information about what is going on in the core of AGNs is spectropolarimetry. Basically you can use the fact that this surrounding obscuring material is scattering the emission coming from the inner parts of AGN, and this emission is polarized. So the polarized emission is giving you really some extra information. So it's another So it's a level up from the spectroscopies to get the spectropolarimetry. And from Afanasyev and Popovich paper in 2015, you can get this very interesting and learn about these very interesting results, how to estimate the mass of the supermassive black hole from the single epoch spectropolarimetric observation. And these results are in very good agreement with the vibration mapping estimates of the supermassive black hole. And this is also a preview for the talk of Luca, which will be given in the next session. And I just want to emphasize that as a part of this Extra Universe project, we are initiating, I mean, this is already initiated, but which will be part of our future investigation, is the monitoring campaign in polarized light.
1
And
minute left, Dragana. Sorry.
yeah, I'm almost done. So with these telescopes, we are going to continue the polarimetric observations. So I'm really sorry that it took me a little bit more time than I planned. And so this is just the summary. I leave you here. So we have submitted the proposal to the Serbian Science Fund about this investigation. And I just want to say that long-term monitoring is important, and it makes a difference, and you can use it for studies of the unseen, of the structure and properties of the broadline region, and as well to estimate the mass of the supermassive black hole. And we all have to get ready for the future surveys. So thank you for your attention.
Thank you very much, Dragana. This was really wonderful review. So we have time for short questions. You may raise your hand, or you can simply unmute yourself. You can also send your question by chat. I'm looking for questions.
Everybody needs a coffee.
Yes, me first.
Including myself.
Yes, too early for astronomers. So if somebody just want to ask question, this is last chance.
Everything was clear.
It was really, really nice talk. Thank you.
Thank you very
Dragana.
much.
So we can, if there are no questions, I cannot see. If there are no questions, then we can go to next speaker. It is Natasha Bon. She is from Astronomical Observatory in Belgrade. And the title of her talk is Searching for Extremely Accreting Quasars. So Natasha, you may share your presentation.
Hello.
Oh, hi.
Just a second. Can you see it?
Yes, it is fine. We can see
so
it.
You can see the full screen.
Yes, full screen is there. We can hear you well.
Okay, okay. So hello, I'm Natasha Bon. I would like to thank the organizers to invite me to give a talk and to present the topic that we worked on and we are still working on. So we search for extremely accreting quasars, and I'm doing it with quite a big team from a different part of the world, from Italy, Mexico, Spain, Poland, and so on. So I think that one of participants, Mariloli, is right here. So she is one of collaborators, and shortly we call our team Extreme Team, since we are working on extreme craters. Okay, so let's go back in 1929, when actually Edwin Hubble gave one of the main discoveries in astronomy, when he found this velocity distance relation, very well known among galaxies, what we found actually is expanding of the universe. It is really huge discovery. And since it is velocity distance relation, so he need some standard candles to actually estimate the distances. And the well-known Hubble constant that he obtained by eye in that time, which is around 500 kilometers per second per megaparsec is quite far from the value that we know today, but anyway, the principle is correct. And let's jump now to 2004, when actually um, another type, let's say, of standard candles has been used. So Kirchner used supernovae type 1a to measure distances. And just here on the, yeah, you can see the cursor here on this plot. I mean, it's old-fashioned plot just to be easy to compare with the original Hubble diagram. And here you can see this red square. It is original Hubble diagram from 1929. So you can see uh, you can see how far we went from that time. So distances are much higher that we can on which we can observe objects. Even in 2004, now we are going much further. And actually, the point with supernovae type 1a is that they have intrinsic luminosity, which is almost constant, and which is about absolute magnitude is about minus 19 when the intensity is of supernovae is when do we have a peak of intensity of supernovae. Uh, so um, uh, from in 2012, actually, there were two projects that were working on supernova cosmology cosmologies, and here you can see in 2012 that supernovae have been found until a redshift of 1.6, but there were only two sources on redshift higher than 1.4. So we will concentrate on this part of the graph, which is below 0 and 1.4. And actually, the point is that until 1.4 we have so we had supernovae or standard candles that could be used for distance measurements. But actually after 1.4 or 1.8, unfortunately we cannot use supernovae anymore, so we need to go further. So we have to find some another standard candle. And of course the 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 natural approach would be to use quasars for standard candles, since quasars are objects that we can see on the highest redshift. So until now, actually, we observed more than 500,000 quasars, and they are most luminous objects in the universe. So they can reach bolometric luminosity up to 10 to 28, 48, sorry, ergs per second, and the most distant quasar observed up to now is on a redshift around 7. But we have a lot of reasons not to use candles of quasars as standard candles. Actually, not to use them, but it is difficult to use them for many reasons. The main reason is that their luminosity is spread over 6 orders of magnitude, and it is something that makes them opposite to conventional standard candles. They are highly variable sources in luminosity and spectral energy distribution, and their spectral properties do not show strong sign of a luminosity dependence. And of course, and they are anisotropic sources. But the goal is to find one or more parameters which are closely related to intrinsic luminosity of quasars, and to isolate class of quasars with some constant characteristics that we can use for redshift independent estimate of luminosity. And there were several attempts to use quasars, but since And they're all using reverberation mappings, and not a Baldwin effect is something different. But okay, I will just list them since I have a lot of slides and I will not have enough time to talk about it. People were trying to use Baldwin effect or the relation between the luminosity in a UV domain and equivalent width of C4 line. Then continuum and BLR reverberation using the RL radius luminosity relation. From dust reverberation, people try to use, since the inner radius of the dust torus is expected to be proportional to the square root of the accretion disk luminosity. Then from X-ray excess variability method from actually, okay, I will not talk about it, but you can see references. Professor Wang actually proposed the method of super Eddington black holes that actually is a similar approach that we are using, but they need actually indirect investigations, actually monitoring campaigns. Um, So here is one very interesting method for using quasars as thunder candles. And it is a method proposed by Guido Risaliti and Elisabeth Lusson. And what they are doing, actually, they use actually a relation. They found a nonlinear relation between fluxes in X domain and in UV domain. They used they started from about 5,000 sources from a 3XMM catalog. They used just sources with high signal to noise. Okay, also I will not go into details since it is not connected with my work, but you can see here, it is very interesting that they actually, here is the distance, and here is the redshift, you see. So they measure fluxes in X and the UV domain, and they measure redshift. And all the rest is actually our parameters in the fit. And they obtain very good Hubble diagram, and these are their parameters, cosmological parameters that they obtain. And on this inner plot, you can see their comparison with supernovae up to 1.4 or a little bit more. The red dots are actually averaged values from their calculations. So this is one very, very good method which can go far up to redshift around 6. And the one that we use the one that we use to try to use quasars as standard candles, actually Eddington standard candles, is based on the actually the theory of thick accretion disk. If Eddington ratio and black hole mass can be derived from some distance-independent measure, it would be possible to derive distance-independent quasar luminosity. Quasar radiating close to the Eddington limit show distinct optical and UV spectral properties that can be recognized in the spectra, so we can select easily the subsample of quasars that could be used to measure standard candles. So, as Dragana already mentioned, the quasars do not all show the same spectrum. We have huge diversities in their characteristics. So here are just two, oh, sorry. Here there are just two different spectral types, let's say. So one is narrow line Seifert 1, and another one is prototype of Seifert 1 Galaxy NGC 5548. So you see huge iron let's say pseudo-continuum. On the blue side of H beta and the free lines, then the line profile between the lines is very, very different. So we can say actually that so quasars are a very I mean we can say that quasars can differ on on so many aspects. So their emission line profiles are different, their shifts are different, the contribution of iron is different, the fraction of stellar population, and so on and so on, the shape of the continuum. It is interesting to try to systematize actually different characteristics of quasars. Something similar to what was done for stars when on a Hertzsprung-Russell diagram. Back in 1992, actually Borson and Green find, let's say, very, very important parameter, which is RFE, and we can obtain it as a ratio between, here you can see between the iron, the intensity of the iron and intensity of H beta line, actually equivalent width of iron and H beta line. Here, and actually they found the correlation between RFE and the full width half maximum of H beta line. Actually, this one is was the first very known. So it is the correlation between the equivalent width of Fe2 and peak of O3 line. This is something that this parameter space there of RFE and full width half maximum of H beta is actually so powerful. You will see you can systematize all diversities of almost all diversities of quasars on it. In 2010, Marziani and collaborators made actually with a higher sample, with a larger sample, sorry, they made actually optical plane, so using the same parameters. But what they did actually, they divided the whole optical plane into beams. So they divided the beams according to RFE, using RFE equal to 0.5, and according to one. So the width of the beam is 1,000 kilometers per second of full width half maximum, and sorry, I'm so slow. So actually, what they noticed, actually, there is a huge difference between these classes, what they call A1, A2, A3. Sorry, I'm showing with my pen. A1, A2, A3, A4, B1, B2, B1 plus, B1 plus plus. So between B1 and B1, A1 and B1 plus plus, it's a huge difference in the width of the line. So here we have lines which are narrow, here are very broad. This difference on 4,000 kilometers per second is also probably due to some change in the creation mode, because the luminosity, the actually L over Eddington here is around 0.2. So on the lower part of the diagram, so sorry, I forgot to say, so we call it the population A, and here we call it population B. So between population A and population B, we have huge differences in Eddington ratio, in intensities, and so on. So I will show it in next slides. So here, just you saw the same spectra that I showed several slides ago. So you see here the narrow line, Seifert 1, which is here, and B1 spectral 5548, which is here. So you can see on this diagram how huge differences there are, and how we can actually show it on the diagram. So in 2014, also Shannon Ho used almost 20,000 SDSS quasars found from SDSS catalog survey, and what they found, actually they made the same plot and actually found, okay, here's so actually they found the drivers could be even accretion efficiency or orientation. So here we have a lower orientations, and here we have higher angles actually. Okay, so here you can see in different beams how different are H beta lines and O free lines. So for example, here we have very strong O free lines, here they are very, very low. Here we have very broad emission lines, here they're much narrower, and so on. Then you can see it in different scales of luminosity. And the same thing that I was talking about. So here you can see actually what are the values of most important parameters where we can differ actually population A and population B. Very important thing is actually that some emission line that we can receive, that we can obtain, are coming from realized flattened system, which is here, which are emitting H beta line and low ionization line, and the one which is from the region which is much closer to the black hole. And besides this realized flattened system, we have also strong winds and outflows. So we can actually make difference in the profile of emission lines depending on the region where they're coming from. So H beta, which is low ionization line, is very symmetric, while let's say C4 line, which is coming from another region, have this strong blue shift. And using virial broadening estimators such as H beta or aluminum line, we can actually estimate virial black hole mass and Eddington ratio. I think the same formula were presented by Dragana. Okay. And Sulentic actually presented some physical trends on the main sequence, where you can see actually that when you're going, so it is interesting that this main sequence has this banana shape, and so when you go, you have a decrease, let's say decrease of ionization parameter, you have increase of the Angeles accretion rate, and you have again decrease of black hole masses and increase of electron densities. And let's come to physical conditions. So Sun and Shan actually found that if we consider actually sigma obtained from stellar population, so from host galaxies, which is actually the proxy of black hole mass, we can see for each luminosity beam that with RFE, so with the highest RFE, as high RFE is increasing, actually that the sigma or M is decreasing. So actually what it means that L over Eddington increases with RFE, and this does not depend on the viewing angle. Besides, a very important result was presented by Pudu in 2016, where actually he found fundamental plane which present the correlation between L over Eddington in function of RFE, but also the parameter D, which is the ratio between full width half maximum and sigma of H beta line. So you can see you can see very good correlation here in this plot. You have XA sources, and I will go back on this after a few minutes. Okay, so both methods imply that the highest RFE corresponds to the highest L over Eddington. And so actually using all of this, we can very easy make selection criteria for extreme population A, which is this green part of the main sequence of quasars. Just using very simple condition that RFE is higher than 1 and about 10% of quasars is coming into this part of the main sequence. And the UV selection criteria are take into account the ratio between lines in UV. So between, here you can see it, so between aluminum and silicon line and carbon line. And here is something very, very important that, as I mentioned before, that in a super Eddington accretion regime, thick disk is expected to develop. What does it mean? Thick disk is optically thick and geometrically thick disk. So the accretion flow remains optically thick, so radiation pressure actually fattens it. And when the mass accretion rate becomes super Eddington, here, when super Eddington, the emitted radiation is advected toward the black hole, so the radiative efficiency of the accretion process is expected to decrease. And what does it mean? It is causing this asymptotic behavior here of the luminosity as a function of the mass accretion rate. And three conditions are satisfied for XA sources, XA quasars. The constant Eddington ratio, we can obtain like this, the virial motion, low ion, and the spectral invariance, which means that the ionization parameter has to be approximately constant. And using these three conditions, we can find virial luminosity equation. So from a virial luminosity equation, we can obtain luminosity. So by a simple measurement of full width half maximum of low ionization line, we can derive that independent estimate of accretion luminosity, and this can be applied to all XA quasars. And this is from Marziani and Sulentic 2004, when they applied on about 19 objects using H beta line and aluminum line. And they got a very good Hubble diagram for quasars, and actually they constrained sigma m much better than supernovae. So probably because the coverage is much higher, so it is going up to 2.5. And to check it on the larger sample, actually, Alan Negrete is the first author of this work. We actually made a sample consist of around 300 objects from SDSS catalog, actually starting from the sample of Shen and Ho, and use those only quasars on a redshift lower than 0.8. Then we use signal to noise, which is higher than 20, and and measure actually RFE and equivalent width of H beta and full width half maximum of H beta after subtraction of continuum, and actually obtain again main sequence of quasars for this sample. And these are results which are very in a very good agreement with concordance cosmology. So here you can see the whole sample, and here in the paper from last year you can see average dots which are in very good agreement. Okay, and what is actually very important? Very important is actually in one of the previous slides you can see that this sample of about a little bit more than 300 sources consists also about 30 galaxies with a very high fraction of host galaxy. And the point is that it has to be distinguished between the fraction or the contribution of host galaxy and iron in the spectra, because if the if uh, if we estimate wrong contribution of iron, then we estimate the wrong RFE, and then we can place the object or the spectra on a wrong place in the diagram. So in that case, we can actually use spurious objects in our Hubble diagram. And this can actually uh, this can actually bring some additional errors or errors in the diagram. So what we did actually, we here I will say something about this first. So we fitted these 30 objects with a high contribution of a host galaxy with Ulyss code that we adjusted for the fit of Seyfert-1 spectra. And we made a simultaneous fit of AGN continuum single cell population, and we used Pegasus in that for that work. Then the FE2 template of Marziani, and so the sum of the sum of Gaussians for emission lines, and fit was performed between 3,700 and 6,800 angstroms, so in a very broad domain, and it was very time consuming. So, but here you can
3
see.
minutes left. Sorry.
Oh my God, sorry. Okay, and what we obtained actually, so the analysis were done very deeply. We were analyzed with Monte Carlo simulations parameter, with chi-square maps, and so on. And here I would like just to emphasize that we obtained the correlation between the width of FE2 lines and the age of SSP. And what we find actually is just one source from that 30 sources with strong host galaxy contamination is a safe XA source, but it belongs to B2 spectral class, and it makes some problems after in the estimation of the L over Eddington. Okay, I will skip this slide. And here just I would like to emphasize that we were trying to obtain L over Eddington for our sample. And actually here we compare L over Eddington from a fundamental plane of Pudu and from virial product. And since and so our actually dots are in this part of the region. We can see actually that according to fundamental plane, we have some objects with high L over Eddington, but according to virial theory, we do not. Actually, the L over Eddington is much lower. So what was the reason for this? Probably because fundamental plane was made for main sequence quasars, and these are outliers, actually almost all. And here we compared actually lower Eddington from using two different methods. So Benzetal and from Virial luminosity without correction. And since I don't have any more time, I will just say fast that we try to make different kinds of corrections on the on the mass and on the RBLR. Okay, so to obtain masses in order to get a higher L over L Eddington. And actually we calculated masses from sigma and obtained actually that we have to make some restriction of sigma, which has to be higher than 150. And these red dots are coming from this. Then we use the corrections for scaling law, actually for form factor of Meyer and Restrepo. And also, actually here you can see this formula, and also we corrected the RBLR according to the formula of Mariloli Martinez Aldama. But again, we get only one source with much higher L over L Eddington. And a proper identification of XA sources. So besides selection criteria based on RFE and ratio of UV spectral lines requires careful multi-component fit that includes the spectrum of the host galaxy, especially if the AGN is of low luminosity. And it is necessary to perform this simultaneous multi-component fit in order to retrieve information of the stellar component and the FE2 emission. So inclusion of these spurious X-ray sources may dramatically increase the dispersion of the Hubble diagram of quasars obtained from various luminosity estimates. Hubble diagram for X-ray quasars is consistent with concordance cosmology and provides better constraint on sigma m than the one obtained from supernovae. And the next step would be to try this on a larger sample. So we can conclude that X-ray quasars might be suitable as Eddington standard candles. Thank you.
Thank you very much, Natasha, for so interesting talk. So we have time for one short question, if there is any. So you can just unmute yourself and ask a question.
Okay.
Participants can just unmute themselves and ask the question. So if there is no any question, we have to go to the next speaker, and that is Nemanja Rakić from Faculty of Natural Sciences and Mathematics, University of Banja Luka. It is Republic of Srpska. So Nemanja, are you here?
Yes, I'm here.
Okay, the title of his talk is Fully Automated Python Tool for AGN Spectra Analysis, Fantasy. So
I'm just waiting for Natasha to stop sharing her screen. So
yeah, sure, but I cannot find the way, sorry.
Okay.
Stop sharing, please go to the up
yes,
to the...
I know how to do it. Okay, I found it.
Is it okay? Thank you.
Okay, so I can share mine. I think this is okay. You all see?
Yes, we see it. It's great.
Okay, hello everyone. It's, as said, it's very early in the morning and it's raining. Not early in the morning, very early, but it's early in the morning and it's raining and it's beautiful weather to sleep here in Banja Luka. And I'm gonna try to be as much concise as I can be, and it's not always successful. I really don't like these kind of presentations because I can only see myself, and I'm having the feeling that I'm talking to myself and no any reaction. So if I become boring and long, please stop me. So today I'm going to present the code that I'm working together with Professor Dragana Ilic and Professor Luka Popovic for some time now, and it's called Fantasy. We have this beautiful logo. I really like this logo, yeah, and I really like the code for now, and I think it's going to get better. So I was planning to say in introduction why we need such a code, but Professor Dragana in the morning lecture gave the actually reasons why we need such a code, because we have like we have the big data astronomy today with new projects are coming with LSST and even with now with the SDSS. We have a lot of spectra to process, so we need much help as we can with some automated tools. We have an increasing number of monitoring campaigns. Professor Dragana mentioned that several times during this morning. Reverberation mapping is in hype these days, so to proper estimate the mass of the black holes, we need the precise measure of the spectral parameters, and that's the reason we need really such a code. We decided to write it in the Python, even it's not the fastest. It's very easy to learn, and it's really widely used in the Astro community. So it's good for scripting language. It's also good for object-oriented programming, whatever someone finds suitable. But I think it's a must-known in this decade for working in astronomy, and also it's applied in the data science community. It's very popular there, so I think it's a proper language to choose to work on such codes. The thing is, actually, the code, I decided to write the code, and I was supported by Professor Dragana and Professor Luka Popovic, is actually when I started working on my thesis, and I had a lot of spectra to fit, to extract the parameters, and it was really boring to do spectra per spectra. And at the beginning I had hundreds of scripts. This script is doing that, then extracting to the other script, and I have like thousands of files keeping somewhere on my computer, and I was like getting lost with all these scripts. And if you change one script, you rename it different, and if you come after 2 months, you forgot what you actually did and what's the result. So it's really important to automate this boring stuff and keep it all in let's say in one script, in one program. You keep all the steps you done with the spectral analysis. It's reproducible. You can publish your Jupyter notebooks, let's say, and it's very easy to reproduce the data, and that's really key thing to do. So we base our code not just by mathematically doing the fitting of the spectra, but actually we include all the physical theoretical findings we have. We decide to use the FA2 model that was written by Jelena Kovacevic and et al. And another thing is also the narrow lines ratios that we have known by theoretical calculations, and everything that's all binded into the code by itself. So one doesn't have to think, is it okay or not? And what's really the plus, it's very easy to use. Of course, you have to know a bit of Python programming language, but not much of it. If you want to change, yes, you have to know, you have to understand the code and everything. And I'm commenting all the parts of my code. It's going to be open source, so if someone doesn't like what I'm doing, he can easily change and write it in the way he liked. Okay, so the code, the fantasy code, I'm gonna make a little demonstration. I have like one case study. I'm gonna show how it actually looks. This is my Jupyter notebook, and we actually first we have to read the module, and there is a one module called Spectra. It has a lot of tools in it. For reading, pre-processing spectra, etc., etc. So we have like to read spectra, we have two methods. It's read fits or read txt. read fits, it's actually made only for SDSS fits. So but we are trying to expand that on much other, but it's really not that possible to guess what kind of fits files it's going to be, what's going to be keywords you need to extract. So it is easy to use any fits opener, any fits module we have on Python, and just convert in the spectral class that we are using in this code. And that's we have these function make spec that actually takes your input and makes it as in the spectral class used by Fantasy. With reading fits, this is for SDSS fits, we have an example. Here we read all the data we need as a redshift, write accession, declination, modified Julian date, and also the all we need in that. And you can, when you are creating your spectra, you can use both of them. You can just assign the values for, I don't know, you can say S1 Z is equal to 0.3, and it's going to accept that information in the from now on. Okay, here it's still the old value, but you can use the because the printing function is actually after after when we change, before we change the value. Okay, so okay, let's continue. So we can plot the spectrum to see if it's read correctly. That's quite easy. We build a function called plot. You just S1 type plots. You give the name, whatever you want to give here, spectrum, and that's it. And you can see it reads also the plate number, fiber, modified Julian date, design. So you can basically use it directly from here. You can just save it and and put it wherever you like it. So the next thing, okay, when you have the spectra, you have to do the galactic extinction, and there are several ways to do that. Okay, just a second. We build it like just a function to read in. That's basically applying the pi astronomy function and using the maps from Schegel et al. And it does what basically in this very easy step. So your flux is already corrected for the galactic extinction, and you can proceed with using just to continue with already corrected flux. Then for the redshift correction, if you like to correct for the redshift, this is the formulas we use to correct for the redshift. In this way, we use the Z value. We already read it from the SDSS fits file, but if you want to change, I already told you and showed you how you can actually change whatever you like. So the function that actually do the correction for the redshift is cored, and it's applied in the very simple way. So another thing, if you want to avoid the host contamination of your AGN, you have to remove the host galaxy contribution. We adopt here the model from using the Eigen spectras published by Yip et al. In 2004, and what he actually did, and Van der Berg in 2005, they explained that you can recreate any AGN spectra by using just small numbers of Eigen spectra of both AGNs, quasars, and host galaxy. So what we are doing, we are fitting our spectra with the linear combination of Eigen spectra provided by Yip et al. And we are fitting the spectra, and we are subtracting the recreated host galaxy. You can see here on that we can plot it easily to see the results. I guess there is also here, yeah. Here is with the orange, the blue is the data, orange is the fit, and the green is the host galaxy. The same here, you can just plot the host, and you can see the spectra subtracted by the host galaxy and the host galaxy that is extracted from the fitting method. The thing is that you have you can always plot again the host, and it's kept the array that's holding the information about the host galaxies is kept through the code, so you can just call it by s1.host, and you will get that array. So when we did with all these steps, of course you need to check also, do you have some outliers and everything else, but this is a quite nice spectra, so there was no much to do before. We have also the tools to rebin the spectra in the way you like it, and I didn't show it here, but it's in the code, and it's going to be in tutorials that's going to be on GitHub very soon. So the next thing is actually the fitting the spectra modeling the spectra. So we have the aging lines and fitting modules, and we have several modules to load before we start with the fitting. So what we have in aging lines, it's a bit tricky. I have to change this because we have the FE2 iron 2 module by Jelena Kovacevic et al. And Bracken power law we used. We have also the power law or the line, whatever model you would like to fit your continuum. And we have the fitting routine we have to input here. We are using the Sherpa. That's quite
5 minutes
nice
more.
API.
Sorry,
What?
5 minutes
What?
more. 5
Okay,
minutes more.
I'll be. I'm close to the end. So we use Sherpa API that's very fast and very nice and very easy to use. And I didn't want to write a new method for fitting because it's not necessary. It's already there. And yeah, so you have to prepare the data in the way that Sherpa understands it, and you can manipulate your data as much as you want. You can put the limits x min, you can put also the I don't know, x max to whatever value you would like, and etc. etc. So we have the data prepared, and the data in this way is prepared to working with the Sherpa module and our fitting routine. Yeah, in this we divided flux and error with 100 because I already had parameters set up for this fitting, so I didn't want to change it much. Yeah. So we are defining the lines. The line is Gaussian form. You can also use Lorentzian form or Gauss-Hermit. It's all available in the code. So the Gaussian is defined by an amplitude, position, and the position is actually the fixed, but what you are varying is actually the offset of the line. It's much easier for that in the code to optimize the position of the Gaussian fast, and it's tested. Believe me, it's better to use with the offset, and you can log the offset to the another line. That's interesting for the when you are modeling the narrow lines in the agent. So yeah, and we are optimizing also the full width at half maximum, not sigma, but full width at half maximum. So first you have to create all the lines you want. Every spectra is different. It's even if it's possible with, let's say, with this parameters I'm going to show you to fit, I don't know, 40% of those spectras, but if you are working with fitting spectra, you have to tweak a bit of parameters, and when you're done with that, then it's great. It's impossible just to use one parameter space and fit all the because you work with the numeric, and the results can be crazy in much of the time. So it's important to tweak with the parameters. It's easy. You just create H beta. You say it's a line. You give the name. You give the position, and you can put constraints on all the parameters. And actually, you can constrain all the parameters fitted. Sometimes it's very important. And we also so we define all the lines, and we import also the FA2 and okay, it's skipped. Okay, we defined FA2. It's a Kovacevic et al. Model for the iron 2, and we defined the power law. We can froze it in one point, or we can put this as a free parameter. It's up to you. We define all the lines we want to have. If it's if we say there is a two Gaussians, we model two Gaussians, you just add another one. You can keep the same parameters. You can just leave this, or you can just write line and open and close the brackets, and it's going to assume the H beta line at the beginning. So you can tweak all the parameters as you want, but you don't need to keep all of this, but you just write whatever you need for that special line, and we create the model. It's in this way. We create, let's say, just broaden lines. In the same time, we define the narrow lines. You can use the mathematical expressions. Let's say if the O34959 is 3 times smaller than or the amplitude of that line is 3 times smaller than the O35007, you can just write in such a way, and it's all working there. And you create the narrow model, and you just create a total model, and you proceed with the fitting. It's in like this line of the code, and it's going to give you the information that's very important information. If you are overfitting, if you're underfitting, if you need something more, if it's stuck somewhere, it's going to give you all the information. You just print those grease result. Okay, so we plot it, and we see the nice AGN spectra fitted in using this way. We are actually thinking to make also the plotting library based on the matplotlib, of course, and just to plot the result in easy way, saving the time of writing all this stuff. But if you want to control how your plot looks, this is a good way you can do it in such a way. So also we adopt the Monte Carlo bootstrap method for the uncertainties. So
1 minute.
we create the random, yeah. Okay, so we create the bootstrap model, and yeah, uncertainties, and you get the result of your fitting in this way with errors. It's a pandas data frame, and also if you have all the parameters extracted from your bootstrap method, it's there. If you want to plot nice parameter space plot with a corner package, it's possible, like I'm showing here. And we expand our code with internal calibration of spectra. If you have a multi-epoch investigation, you need to do internal calibration. We adopt the false null method, and it's also one line of code in Fantasy, so it's quite easy to do. Yeah, and okay, I'm at the conclusions. I'm gonna finish soon. I showed you already, and Professor Draga in her lecture explained why is such tool needed. It's written in Python, and it's open source. It's easy to module and change in like however you like. It's developed for the single epoch and multi-epoch agent spectral analysis. And to do, we have to expand reading section of the code, so we can deal with another FITS formats. We are planning to expand the models, adding some new models to analyze light curves, and whatever whatever else. So if you have any ideas how to improve our code, please contact me. My mail is here, so I would really love to hear what you think about my code, and if you have some ideas how to improve it or expand it, I'm here to hear. Okay,
Thank you very much. Thank you very much, Nemanja. I will try your code, it's for sure. So we have time for one short question. Is there any question? You may unmute yourself and just ask a question.
Yes, actually. Here's
Yes.
Vladimir from Department of Astronomy.
Yes.
Hi, Nemanja, very nice talk. There is only one short question. Have you tried to parallelize the code? Is there a need for doing that?
Parallelize the code.
Yes, yes.
Yeah, that's what I'm thinking how to do it. It's we can parallelize all the steps if you're doing multi-epoch. If you're doing with hundreds of spectra, it's easy to parallelize. But fitting procedure is quite hard to parallelize, and it's actually done a bit by Sherpa API. I'm not sure, but it's really hard to do it. And I'm thinking the way if you're doing one single epoch, but it's usually not needed because it's quite fast when you fit. But
Yes.
if you are doing on the multi-epoch, yes, you can parallelize to course you want to use. So that's also built into these multi-epoch thing.
Okay, great, because it's pretty easy to do it with inside Python.
Yes, it's quite easy.
Okay, thank you.
Okay, we have no time for more questions. We are going to the next lecture. Thank you very much, Nemanja, once more. So next lecture is Isidora Jankov from Faculty of Mathematics, University of Belgrade. And she will talk about manifold learning in the context of quasi-spectral diversity. So Isidora can share her presentation.
Yes, thank you, Jelena. Just a second. Can you see the presentation?
Yes, we can see it. You can proceed.
Okay. Hello, everyone. My name is Isidora, and I am a second-year PhD student. And I would like to tell you something about the things that I have been working on during my first year of PhD, together with Professor Dragana Ilic and Professor Anđelka Kovačević. The topic of my talk is manifold learning in the context of quasi-spectral diversity. So first of all, I would like to say a few things about manifolds and manifold learning. What is it? So in mathematics, manifold is a topological space that locally resembles a Euclidean space, but its global structure can be more complex. So the most intuitive and easiest example of a manifold is a sphere, like a surface of planet Earth. So locally, you can measure distances using Euclidean metrics, but if you want to measure some large distance, like a distance from Belgrade to Beijing or something like that, you need to use different metric. You need to use geodesic distance and so on. So this is one example. Another example of manifold is a torus or double torus, or some interesting shapes like a Klein bottle and so on. And why manifolds are important? Besides being just like some kind of mathematical curiosity, they're important because of something called the manifold hypothesis. So it says that in real world high dimensional data, most relevant information is concentrated in small number of low-dimensional manifolds. That actually makes sense because real-world data based on physical laws. So if you measure various parameters in a high number of parameters for some object or something like that, the measurements will occupy just some subspace of that whole parameter space. So it is a good approximation to assume that this subspace is some kind of a manifold. And that was tested theoretically in the paper of Pfefferman et al. And empirically by Carlson. So having this mathematical knowledge, we can use it to learn something about our real-world high-dimensional data. And we can do that by using manifold learning. And manifold learning is a class of unsupervised machine learning algorithms and techniques that can learn the geometry of the manifold that is embedded in the high-dimensional space and project it to a lower dimensional space while preserving the original relationships between the points. So manifold learning is just another term for nonlinear dimensionality reduction. So on the one hand, you have nonlinear dimensionality reduction. On the other hand, you have linear dimensionality reduction. And most famous technique of linear dimensionality reduction is principal component analysis. And many of you may had experience with it. So why this dimensionality reduction is important? First of all, it's important because of the so-called curse of dimensionality. That is something that appears in large data sets. And for example, if you have some high dimensional data and you want to take some subsample from that data, as you add more dimensions, the statistical significance of that subsample will go down, and you will need to add more data to compensate. So that can be very big problem for like SDSS data or some large data sets like that. And also dimensionality reduction is useful for it needs less storage space on a computer. It needs less computing time for running algorithms then. And it is very useful for visualizing high dimensional data also. And that is something that we've done on some data. So here you can see another example of a manifold. And just to demonstrate what those algorithms do, they just, we have, for example, this is like a two-dimensional sheet that is rolled in this Swiss roll shape and embedded in the three-dimensional space. And those algorithms can actually find that if some parameter goes along this curved surface, they can find that we have a redundant dimension, and it can unroll this Swiss roll and present it in two dimensions and remove the third. So it is good for dimensionality reduction, and these algorithms are useful for visualization or for pattern recognition, like facial recognition on images, and also for classification tasks in astronomy and in other disciplines also. They're useful for revealing nonlinear relationships between parameters because nonlinear relationships are preserved when you project data from high dimensional space to the lower dimensional space. So here I just wanted to explain that how nonlinear data is transformed by linear dimensionality reduction and nonlinear dimensionality reduction. As you can see, when we have nonlinear data, linear dimensionality reduction techniques are not that good. They cannot recognize that the direction of the highest variance is across this curved direction. So, but non-linear dimensionality reduction techniques can identify it. Then I also wanted to give you some feeling how these manifold learning techniques are used in astronomy. And they're used basically primarily for classification. And one of the first papers that introduced one of the algorithms, the locally linear embedding algorithm, to the astronomical community is the paper from Van der Plas and Connolly. And they used this manifold learning algorithm to classify Sloan Digital Sky Survey galaxy spectra. And this is just one projection from a 3D, originally 3D projection. And you can see that they were able to identify broad-line quasars, narrow-line quasars, emission galaxies, and quiescent galaxies and absorption galaxies can be seen in the other projections. Then these techniques are also used for classification of SDSS stellar spectra, for classification of eclipsing binary light curves, also for identification of different types of peculiar stars, and their separation from normal stars using Rave spectroscopy survey data, and so on. And you can see that it is used quite often, but not overwhelmingly often in astronomy. And here, the second part of my talk is about how we applied manifold learning on which data and so on. And as Natasha Bon already said and explained in great detail, that quasars occupy, there are several populations of quasars. They can be defined in the eigenvector 1 parameter space. And so in this parameter space that is defined by this equivalent bit ratio of iron and a broad H beta line and the full width maximum of H beta line, we can define something like a main sequence that is analogous to the main sequence of stars. But here, the position of a quasar here is determined by the accretion rate of the material onto a supermassive black hole. And that is something that is parameterized by Eddington ratio, and also depends probably on the line of sight orientation of the source. So the sources that belong to the same populations exhibit similar spectroscopic properties, as Natasha said, and broad line physics and geometry. So what we wanted to do is to expand on their work, on very detailed work in the past 20 years, and to see how this manifold learning classifier can separate those populations when we introduce some other spectral properties also, and to see how those populations are separated in this space with maximum preservation of the original manifold geometry, and also to test how well the Eddington ratio correlates with the main sequence in this space. So the algorithm that we used is called locally linear embedding, and this algorithm can be explained in non-mathematically in the following way. So you imagine that a manifold is a kind of a union of structures that are patched together, and every patch is approximately locally linear structure. And every point on that patch is a linear combination of the nearest neighbors. And the algorithm optimizes the weights in this linear combination so they can reconstruct the original point coordinates. And so in these weights, the geometry, the information about the relationships between the points is encoded. And then in the last part of the algorithm, it fixes the weights and tries to find the coordinates of the projection in the lower dimensional space. And And in this way, the geometry is preserved as much as it can be in the lower dimensional space. And in this algorithm, the free parameters are output dimension, and that is usually 2 or 3 if you want to visualize the data. But in the best case scenario, it must be an intrinsic dimension of the data. But that is it is not very easy to determine that. And we just use 3 dimensions to be able to visualize it. So, and the other parameter, free parameter, is number of nearest neighbors. And that one is very important because when you define these nearest neighbors, and when you define those weights, you must use correct the best possible number of nearest neighbors, not too small and not too large. So here I will say something about the data that we use and how we determine this parameter K. So the data that we use are low redshift type 1 quasars from the Sloan Digital Sky Survey Quasar Catalog with measured spectral properties. And when we apply this constraint of redshift, and when we chose that we have these measured optical parameters, we ended up with a sample of 3,720 objects. And we use some parameters that are probably related to this main sequence. And this is like 10 parameters. So we did a dimensionality reduction from 10 to 3 dimensions. And about this K parameter, number of nearest neighbors, we chose this parameter by we ran the algorithm for a range of values for this parameter from 4 to 30, and actually 29. It is a mistake here. When we ran it, we wanted to somehow compare the relationships between the points, the geometry in the original space and the projected space.
5 minutes left. Sorry,
okay,
5 minutes.
Thank you. So we wanted to compare this geometry, and we did that by using by calculating the geodesic distance matrix for each of these iterations for the original space and for the projected space. And because those matrices, because there's equal number of points in both spaces, we then compare to those matrices, and they have the same dimension, and we compare them, and using RV coefficient, that is a correlation coefficient for matrices. And when we applied this, we got the highest correlation for the K of 12. And then we use this number and dimension of 3 as free parameters, and applied it to our data of this number of objects with these input parameters. And the results that we obtained is we have this separation of populations also in this space, and populations and also the main sequence can be identified in identified in this direction. Now it's like a kind of a linear direction, not a curved one, and the populations, we see this extreme A of population, then the intermediate population A, and the population B. And I would like to emphasize here that these axes don't have a physical meaning. They are just there to give values to coordinates. And the meaning behind this is found in the relationships between the points, as I said, because the geometry of the manifold and relationships between the points are preserved from the original 10-dimensional space, and they are preserved in this 3-dimensional space. And here we, on the right, here we wanted to check how the Eddington ratio changes in this space also. And as you can see, it is correlated with the main sequence, and the extreme A population has the highest Eddington ratio, meaning that they are highly accreting quasars. And on the other hand, on the other side, we have a low Eddington ratio, meaning the low accreting quasars occupy that part of the space. So that is our small contribution, and this is a very early work. And some of our preliminary findings is that we proved to be that this locally linear embedding algorithm proved to be a useful tool in data exploration and identification of objects with distinct spectral properties, and that is also it is possible to find 3 eigenvectors that give projection in 3D, and that contains more information that is potentially lost in the 2D projection. And quasars and the main sequence was identified in this space with the highest possible preservation of relationships between the points. And it is also correlated with the main, Eddington ratio. And some of our future plans is to include more spectral parameters as input for this algorithm, and to see which ones are going along the main sequence, which ones are not. And to also, it is very important to apply this to more recent spectral data that is already available. And to we also want to maybe test this technique in other classification problems in astronomy. That is something that we're thinking about. And yes, that is everything I had to say. And thank you so much for your attention. And if you have any questions, please don't hesitate to ask.
Thank you very much, Isidora. It will be very exciting to see the outcome of this research when it comes. So are there some questions? You can simply unmute yourself and ask a question.
Yelena, this is Swayam. Can I ask a question?
Sure.
Thank you, Isidora. Very nice talk. I was wondering, for this decomposition that you showed in the three-dimensional space, is it a way to show somehow what these eigenvectors in a way correspond to real quantities? Like, which are these three, let's say, eigenvectors that can be associated with physical quantities somehow?
Yes, that is something that is very difficult to determine, because those, like in principal component analysis, also here it's even harder because these eigenvectors don't have per se a physical meaning, but we are working on figuring out how to determine it. But we can vary some parameters and see how they are behaving in this parameter space, and to see which directions are important. Like the main sequence has some direction in this space, but it's not along this axis that is projected.
Great, thanks. And is there any reason behind having 3 dimensions, just choosing 3 dimension and not really probing higher dimensions?
We just use 3 dimensions to visualize the data. That is why I didn't understand the question.
Yes, just so my meaning was like whether there could be actually some important information lost if we do not consider the higher dimensions. Like what we see in the PCA is that one could have a little more than 4 parameters, eigenvectors that could really be associated to give up to 90% of the, let's say, correlation in this space. So that was my question, yeah.
Yes, but we didn't include in the input parameters all of those 4 dimensions that are used for definition of 4D eigenvector space. But yes, it is always we will always lose some information. But yeah, I don't know how to answer. But I will try to think about it more.
Great, thank you. Thank you for the nice talk.
Thank you very much for the question, and thank you once more to Isidora for the talk.
Jelena,
yes?
Sorry, quick reminder of organizers for you as a chair that we have 40 minutes of talks, and the next session should start at 11:50. So please run the session up to 11:40.
Okay.
Is it okay?
Yeah, sure.
Okay, thank you.
Okay, now it's time for the next talk. It is Marina Manganaro, Department of Physics, University of Rijeka, Croatia. Hi, hello. And the title of her talk is The Intermittent Extreme Behavior of BL LAC 1ES 2344 plus 514. So, Marina, you may start your talk.
Okay, now I'm sharing my screen and I'm not sure it is visible. Can you please tell me if it's working?
Everything looks good. We see it.
You see the full page?
I believe it's it. We see full page. No, actually.
It's not full. Okay. So let me try again. Okay. Maybe now it's full. Okay, I'm sorry because I don't have control. I mean, I don't know how you are looking, but I suppose that now you can see one slide, right?
Yes, yes, it is.
Okay, okay. So thank you very much for giving me this opportunity to talk at this conference. I'm very excited because I know it's common to speak about my work with a lot of people, but this is the first time that I'm talking to a restricted group of people which is close by to my university. So I really hope that sharing with you my latest study could be useful to have some collaboration with some of you, because even if during this COVID situation we are relatively close, I work at University of Rijeka. Okay, so I'm presenting you today a work that I published a few months ago for the MAGIC collaboration. And you can see in this first slide, I worked with many people, not only from the MAGIC and FACT collaboration, but also with a lot of multi-wavelength collaborators. So this is also why I am happy to share this work with you, because all the things that I do normally for my research are done in a multi-wavelength context. So I hope to find also people in other bands like optical, for instance. I know that there are a lot of people working on in the optical band here, and maybe in the future we can work together. So what is the point? Okay, I will talk to you about this intermittent extreme behavior of this source, which is a kind of BL Laserte source. Okay, and I explored this source with different instruments. Basically, I work with the MAGIC telescopes, so I work in very high energy gamma ray range. And also FACT telescope, which was our partner for this research, is working on very high energy photons. But of course, if you want to cover multi-wavelength observation, we need to work with many other telescopes and gather all the data together from the same source, possibly at the same time, so we can have a description of the emission scenario, which is kind of simultaneous. Okay, so now I will move to my second slide, which I hope it's visible. Okay, here I present very briefly the MAGIC telescopes. I don't know if you, probably you have heard about them. So MAGIC stands for Major Atmospheric Gamma Ray Imaging Cherenkov telescopes. So MAGIC telescopes are actually, they are optical telescopes, because what we do is to detect a light which is in the blue band, because it's Cherenkov light. So it is visible. Maybe it's too fast to be visible by the human eye. So we need these giant telescopes with all these mirrors, but is visible. The problem is that, differently from an optical telescope, what we are doing is to collect this blue Cherenkov light, which is coming from a shower of particles. So this means that if you collect Cherenkov light coming from a shower, you don't have a very, how can I say, resolved signal, but you have something very spread like a potato. So we cannot dream about to have something like you can get from an optical telescope in the sense of resolution of the image, right? Okay, but anyway, magic telescopes as for this kind of telescopes, which are Cherenkov telescopes, they are pretty performant. So here you can just see a summary of what magic telescopes can do. So they have this mirror diameter, 17 meters of diameter. They have this field of view, 3.5. So I know it's not fantastic, but for our kind of telescope is great. We have this angular resolution, 0.1 degrees, and the energy range that we can cover is, as I said, very high energy gamma ray photons. So it's from 50 GeV to 50 TeV. Basically, we could cover this range, but okay, so these are my telescopes, the ones that I use often. But for this work, we partnered with FACT telescope, which is another Cherenkov telescope very close to us, so our neighbor. And okay, here you also have details from FACT, but okay, we will get, these are just details of the performance, so I would like to be quick so we can go to the point. And here we have the third slide, the multi-wavelength coverage. So all the telescopes that we communicated with, and they provided us their data, so we could make this study in multi-wavelength. So we have Fermi LAT, Large Area Telescope, which is not ground-based like us, but it's on a satellite, on Fermi satellite. We have SWIFT for X-rays and SWIFT-2 for UV. And then we used our friends of Webb because they coordinate a lot of optical telescopes, so we could get data from them. We usually work with them. Then we have some data from KVA, which is an optical telescope in the Tuorla organization of monitoring of blazars. And then Kite telescope, which is a new friend of us. We started to communicate with Kite recently, and they have fantastic coverage of many sources that we are interested to, very well sampled. Okay, so these are our friends in this work. And then I just remind you on about blazars, and blazars are targets which are very important for us, that we work in very high energy gamma rays, because they can emit in our energy range. So blazars are basically AGNs which are pointed toward the observed. So which jet is pointed toward the observed? So having this jet which is visible, which is pointed in our direction, makes easier to get very high energy gamma rays. Of course, this is very generic description, because there is an emission scenario behind. So it's not just very high energy gamma rays, they come from the jet and that's all. But it's very simplified explanation. But okay, in general, blazars are very interesting for us. And here in the left part of this slide, you can see the fingerprint of every blazar, which is the fingerprint of every astrophysical source. I mean, in multi-wavelength. So if you put together, as you already probably know, okay, I'm sure you know, if you put together all the information in different wavelengths, then what you get, the spectral energy distribution of all these instruments, that all the instruments provide you, they have this shape, this double peak in the spectral energy distribution. And from that, you can distinguish different kind of blazars. Well, okay, to be quick, our blazar, the blazar that we studied in this paper, is a BL Certe, and it has emission in the very high energy, and it is an intermediate BL. Okay, it was defined as an intermediate BL, but then what is interesting about it is that when we studied it, it was in an extreme state. What does it mean? An extreme blazar is a blazar which very high energy emission is shifted on the highest energies. So this double peak that you see here, it's shifted towards our higher energies. So if you study the peak of those two bumps in extreme sources, the bump which is indication of the very high energy is shifted towards even higher energies than usual for this kind of source. So what happened? This source, some years ago, it was defined as extreme. Then for other years, it was a normal BLAC. And then now again, when we observed it in 2016, we found it. We detect that in the very high energy gamma rays band, and we found that it was extreme again. So what is interesting about this is that why this source is so intermittently extreme. What does it mean? Of course, we we are not sure because it's very different to categorize blazars, but of course it was interesting because we could see this huge shift of the inverse Compton peak. Okay, I will not talk about the blazer sequence, but it's like a way to study this in general, trying to categorize blazars. Okay, but we know now that our blazer is extreme in this particular state that we observed. Okay, so as I said, blazars are extreme when they have this extremely energetic synchrotron emission. They have very high energy emission extending to several TeV. Their synchrotron peak is located beyond the soft X-ray band, and they show X-ray spectrum variability. This is one important feature of an extreme source. Okay, and then in slide 6, you can see some summary about this source that we presented in this paper. It is an extreme HPL, and it was discovered in 1995 by Whipple. Then it's relatively close redshift, and then the flux, the historical maximum of the flux when during the first observation was 63% of the Crab Nebula flux, and we use Crab Nebula flux as a standard candle for very high energy gamma ray studies. Okay, so since it was interesting in when it was discovered in 1995, yes, then a lot of multi-wavelength campaigns were organized, but the source was not found to be extreme again until this study that we made in August 2016. So here in slide 7, you can see a spectral energy distribution of this source that was published in 2011. And here, these data are not very simultaneous, so it's difficult to describe this emission scenario. But anyway, the authors tried to describe a possible emission scenario. And this that you can see here is a simple synchrotron self-Compton, and looks that it can describe this source. But anyway, this was done in 2007-2018 multi-wavelength campaign. And you can see that there are two different flux states. One is 7.6% of Crab Nebula, and the other is 48%. Okay, but this is what was done before. Also in 2008, another paper is describing the multi-wavelength campaign, and they did not observe extremeness. So they didn't see a shift respect to the historical maximum of the spectral energy distribution that was kind of built during the historical maximum. So what I want to say is that in previous studies, this source was not extreme, but now it is again. So this is why we call in the paper intermittent. And the paper that I'm talking about, and I'm making such shameless advertisement, is this one, Achari et al. That you can see slide 9. So I hope you can go and have a look if you are interested. Okay, so this source is extreme again. So what did we do? We gathered a lot of data, as I said, multi-wavelength data, and then we decided to build a spectral energy distribution with the most possible simultaneous data, because we wanted to catch this source during a high state. a flare, because it was flaring in our energy band. Okay, so we put together all this data. Of course, here you can see slide 10, this multi-wavelength light curve. We have on top very high energy gamma rays, and then going down to the other energy bands. So the last one is radio. And then the pink area is the area that we are considering for the flare. So we had the trigger from FACT telescope that told us that there were high photon for this source, and then we started to observe, and then we got the detection in this red ellipse. I mean magic, but then we have all this data collected by other instruments. So in slide 11, you can see the variability of the X-ray spectrum, which was important for us to determine the extreme state. So here you can clearly see how the spectrum in X-rays was variable. And the behavior looked like harder when brighter. But, you know, we have many measurements, so it's not easy now to see all of them. But anyway, the variability is possible to be seen. And then we checked the archival data, and we built this spectral energy distribution, and we found that our detection was 60% of the Crab Nebula flux. So this source is extreme again during a period of high flux, which is very similar to the historical state, to the historical flux. And we of course worked to locate the synchrotron peak, because from the position of the synchrotron peak we can define the extremeness of the source. So this plot that you are looking here is one of the first plot that we produced with the archival data, and here you can see the in this bump for the host galaxy contribution. Okay,
excuse me, 5 minutes left.
Okay, when you see this huge host galaxy contribution, of course, you probably know better than me that this means that you have to process your data properly to exclude the host galaxy. So our collaborators in the optical band, they helped us to clean this data properly, and this is the final spectral energy distribution. And in this case, spectral energy distribution is modeled with the synchrotron self-Compton scenario, but it was not enough precise for us. So after defining precisely the position of the synchrotron peak, and after studying in details the spectrum in the very high energy, and comparing the spectrum with all the previous studies in very high energy, we came out with an hadronic model. I mean, our theoretician came out with this, applied this hadronic model on the data, and that this was more successful. So what is the difference between the initial model? Here we have also an hadronic component that produces very high energy and defines better the peak of the very high energy. So we were more happy with this model. Here you can see all the details of it, but you can also see in the paper. And okay, as a summary, I just wanted to tell you about this nice result, which was done in multi-wavelength. We found the source extreme again, which is very interesting because extreme sources in our community are interested also because they could emit neutrinos. Okay, it's not the case, but it could be. So extreme sources are very hot topic in our community. And okay, the source is again extreme with the shift of the position of the synchrotron peak towards higher frequencies. And this demonstrates that being extreme is a temporary characteristic of this source. So it could be extreme, but not, depending on okay, it's not very clear on what, but but it's intermittently extreme. And then we defined the magic alpha index of the very high energy spectrum. we studied the variability of X-ray spectrum, which was very interesting. And then for the first time, we constrained the inverse Compton peak, meaning we constrained the very high energy, the high energy and the very high energy part of the spectral energy distribution, because there were no data in the very high energy gamma rays before. And then we have leptonic and hadronic models that both describe successfully the data, but the hadronic model is slightly favored. Both models implied significantly different magnetization of the emitting zone. What does it mean? That we would like to study more to try to understand this, this kind of issue. So we need more data. And that's all. I hope that you liked this talk and you are interested towards what we do at the University of Briega. And if you have any question, I will be happy to answer.
Well, thank you very much for very interesting talk. We have time for one short question. You can participants can just unmute themselves and ask the question.
Hello, Jelena. I just have a quick question.
Yes,
Hi,
yes.
Marina. Thank you very much for this nice presentation. Really interesting source. So what kind of data do you need? I mean, do you need the monitoring data? Would, for example, optical monitoring of these objects from Vidojevicz would be interesting for you?
Yes. In fact, I was kind of also thinking of you, because I know that you have this optical telescope. And yes, what we are doing right now is we are preparing proposal for MAGIC. And the proposal for this source is, of course, in multi-wavelength, because we need multi-wavelength data. So if you have possibility to observe this source, that would be great, because you could join our proposal, for instance, and we can use optical data from your telescope, and we can in the monitoring, because our proposal is about monitoring. So we will monitor this source for the next observational cycle. So yes.
Okay, thank you. We can talk more about this.
Yes,
Okay, thank you very much.
Great. Bye.
Thank you once more. Thank you.
Can I have a short comment on this?
Okay, okay.
Okay, just to know that there is a group in our observatory, and we are collaborating with WEPT group since 2013. So we are, to say, regularly observe magical alerts and so on through WEPT group. So this is just a short comment on Dragana's question.
Yes, WEPT, it's an amazing community. It's fantastic. Sometimes we have alert and we contact them and we get immediately feedback. So I really love WEPT community.
Yes. Yeah. So we are already in some kind of, let's say, collaboration with you indirectly. Okay.
Okay.
Great.
Thank you.
Thank you very much for questions and comments, and thank you once more to Marina for a nice lecture. And now we will proceed to the next talk. It is talk of Michal Bilek. The title of talk is The Matlas Survey of the Faint Outskirts of Bright Galaxies. So do we hear? Okay, nice. You may share your screen.
Can you see my screen?
Not yet.
Not yet.
I forgot to say, Professor Bilek comes from Astronomical Observatory Strasbourg, France. So you may start your lecture. We see it now.
Yeah, you see. So great.
Yes, yes.
Okay, fine. So thank you for introduction. Well, but I'm not a professor yet. I'm just a postdoc. Well, this is just a small correction.
Sorry.
So thanks for introduction and giving me the opportunity to speak at this conference. So what is meant by the title of the presentation can be seen from this pair of images. The left one comes from the Sloan Digital Sky Survey. This survey covered a large portion of the sky, but it captured only the brightest parts of galaxies. On the contrary, our MATLAS survey targets only about 200 galaxies, but it reaches a much better depth. So it also captures the low surface brightness parts of galaxies. And this is advantageous when we want to investigate how galaxies form. The development of MATLAS was made possible because of the development of a technique called deep imaging. Deep imaging is a relatively new way to explore the world. When microscope was invented, we could start observing objects with a small size. When telescope was invented, we could start exploring objects with a small angular size. In analogy to these revolutionary discoveries, deep imaging allows us observing objects with low surface brightness. But unlike in the previous two cases, deep imaging was not enabled because of the invention of some new instruments, but rather because of developing dedicated observing strategies and data processing techniques. The first applications of deep imaging appeared in 2009. Originally, the necessary instruments had already been available before, the necessary telescopes and CCDs. But originally, when people wanted to take a deep image of an object, they just placed it in the center of the field of view and observed for as long as possible. Then followed the standard calibration by bias, dark frame, and flat field. But if you do it, you encounter problems. So let me explain. So the objects with the lowest surface brightness that we are able to capture today have around 29 or 30 magnitudes per arc second square. This is really very low. This is about 1,000 times fainter than the brightness of the night sky at the darkest places of the world. You can imagine that separating the small useful signal from the total signal we receive is extremely sensitive to systematic errors. The most important systematic errors are the imperfections of flat fields and also the parasitic light. The parasitic light is the light of the sky reflected from the walls of the tube of the telescope and falling to the CCD chip. The errors of the second or third order of importance are the variation of the brightness of the sky during the night and also the light scattered on the optical elements of the telescope. These are the so-called light wings of the point spread function. On the right, we can see an example of an image that was calibrated in the standard way. It shows this spiral galaxy M101, and the brightness scale of the image was adjusted such that it visualizes just the faintest parts of the image. The bright blob here is an artifact caused by the systematic errors. So this defect makes it impossible to detect any diffuse extended structures that could be in the galaxy, such as the stellar halo. So, okay, what can we do with that? What is the magical method to cure these defects? So now you will know these 4 images come from our ongoing project with the Milankovitch telescope that we collaborate on with Anna Vudragovic and Serjan Samurovic. The galaxy we want to observe is marked in each frame by the red circle. The basis of the deep imaging method is to take a lot of images of the object such that the object falls every time at a different location of the CCD chip. When the images are taken, we start with the standard calibration by dark frame, bias, and flat field. And then comes the second key step of the deep imaging method, and this is to calculate the median of all these images for every pixel. The median image doesn't show any object because a given pixel captures only blank sky in most of the images. The median image shows only the variations of the background because of the systematic defects, systematic errors, like the blob we have seen in the previous slide. The median image is then subtracted from the original images, which makes their background perfectly flat. The median subtracted images are then co-edited in the standard way and to produce the final image. Obviously, the shifts between the individual images that we perform by moving the telescope have to be larger than the object we want to capture in order for this method to work. So, okay, so what can be detected using deep imaging, and why is deep imaging useful? So we will learn it from the next part of my presentation, which is on the MATLAS survey. The MATLAS survey is a deep imaging survey targeting almost 200 nearby elliptical and lenticular galaxies. The images were taken with the MegaCam camera at the Canada-France-Hawaii telescope that has a diameter of 3.6 meters. The images reach the surface brightness limit of almost 29 magnitudes per arcsecond square. We have between 2 and 4 bands for photometric bands for every galaxy. The galaxies are really well known because MATLAS is a part of the Atlas 3D project that aims to collect all possible information about its targets. One of the main questions we want to answer about galaxies is how they were formed. There are two main channels to form a galaxy. The first is the formation of stars directly in the galaxy, and the second is galaxy merging. Galaxy merging means that two pre-existing galaxies merge, that they collide in order to form a bigger galaxy. The main purpose of MATLAS is to look for signs of past galaxy mergers. They are the so-called tidal features. So in this picture, we can see an example. Here, this small galaxy is being accreted by this massive galaxy, forming this faint stream. This stream is in one of the types of tidal features, and it will remain visible in the big galaxy for several billions of years. We are going to see more examples of tidal features in a few moments. However, other interesting objects can be seen by MATLAS because they fell coincidentally in its field of view. They can be spark galaxies, dwarf galaxies, or globular clusters, and others. And maybe we would discover also something unexpected. So when the images were taken, they were visually inspected and classified typically by 6 people per galaxy. The participants of our classification had this internet image viewer at disposal. It is now available publicly at this address that is written at the bottom of each slide of my presentation. So please feel free to visit. I can really recommend. There are some very nice images. So in this image viewer, we can zoom the image, we can change the brightness and contrast, and we can, for example, display the maps of color index to display the radial velocities of galaxies and others. The participants of our classification were asked to fill in this questionnaire for every galaxy, and here for every structure, morphological structure of interest, they had to fill in whether it is not present in the galaxy, it is likely present, certainly present, or we are not able to say. And if the structure is present, then also the number of such features in the given galaxy. Now I am going to show you the examples of the most important or interesting features that we were looking for. So here we see an example of a star stream. It is this long thin structure. As we have seen, star streams formed by accreting of small galaxies. The small galaxies are disrupted by tidal forces, and so these streams witness galaxy mergers of a mass ratio of, say, less than 1:4. Tidal tails are somewhat similar to streams, but they are thicker. It seems that we have at least two types of tidal tails in our survey. The first one is formed during collisions of two comparable galaxies, where at least one of them is strongly rotating, such as a spar galaxy. The second type of tidal features forms when the galaxy in question is being disrupted by a more massive neighbor. Stellar shells are these arc-like azimuthal features with a sharp outer edge. They are results of galaxy mergers too. In order to form shells, we have to have almost radial merger, and it seems that the most favorable mass ratio to form the shells is 1:4. But all of these tidal features have a limited lifetime. Like everything in the universe, even tidal features relax toward an equilibrium state, which means for a galaxy toward an ellipsoidal or a disc-like shape. But we are still able to trace the, the imprints of old galaxy mergers, even if the galaxy is almost relaxed, because its outer isophotes are not elliptical, but they are irregular, like in this galaxy. Some irregularities can also be induced by distant flybys of neighboring galaxies, like this one. So in this particular galaxy, the irregularities were probably induced by both channels. So this was enough for tidal features. So our survey has detected also some interesting phenomena. The targets of our survey, the elliptical and lenticular galaxies, are characteristic by their old star populations, but some of them reveal these faint rings of young stars. So it seems that there was first the center of the galaxy formed, then there was a large gap in star formation, and then the star formation was renewed. The origin of this phenomenon is still not understood well. Our images also capture these clouds, which are called galactic cirrus. They are dust clouds in our own galaxy. We don't like them because they complicate the classification of the morphological structures in the galaxy of interest. However, our images have already proven to be useful for investigating the processes in the interstellar medium in our own galaxy. Moreover, we found that the occurrence of galactic cirrus correlates very well with the maps of extinction. So maybe these images will lead to construction of new extinction maps with a much better spatial resolution.
Excuse me, 5 minutes left.
Thanks. So the results of the first results of the MATLAS survey have been published in this paper. Its main purpose was to provide the census of various morphological structures in the galaxies. So for example, for shells, we can see that we didn't detect them in 84% of galaxies. They are likely present in 5% and certainly present in 12% of all galaxies in our sample. In total, we found any signs of galaxy merging in between 30 and 40% of all galaxies. We also had a look on the correlation of the signs of mergers with the number of neighbors that the galaxy has and the mass of the galaxy, and we found the expected result. So if the galaxy resides in denser environments with a lot of neighbors, then it has more signs of mergers, simply because in dense environments mergers are more frequent, and also more massive galaxies have more signs of mergers, because more massive galaxies can attract the galaxies to be accreted from larger distances, and they have stronger tidal forces. In the future, we plan to compare these statistics to the simulations of galaxy formation, and also for investigating the formation of galaxies from a purely observational point of view. For example, we currently work on the origin of slow rotation in elliptical galaxies. Most galaxies, including the elliptical ones, show some ordered rotation, like in the example here. Here we see the field of radial velocity, but the galaxy on the right doesn't show any substantial rotation. It is supported mostly by the velocity dispersion of its stars. And we already found out that the slow rotators contain more signs of galaxy merging than the fast rotators. And this agrees with the prediction of the simulations of galaxy formation, which indicate that slow rotators form by mergers of fast rotators. In the rest of my talk, I'm going to summarize or review our deep imaging efforts at the Milankovitch telescope. This famous image was published in 2009. It shows an edge-on spiral galaxy that is wrapped by a stellar stream. The image was taken by an amateur astronomer with a small telescope. Since that time, the same structure was observed by other amateur astronomers. So it was shocking when professional astronomers reobserved the galaxy, and they detected with a telescope optimized for deep imaging, and they detected this simple morphology of the stream. So we were the first to confirm this simple morphology of the stream with the Milankovitch telescope, and since that time, everyone, including the amateurs, detect this simple morphology. Now I am coming to our second paper with the Milankovitch telescope. There is an enigmatic population of unresolved H1 radio sources in the Virgo cluster. They are atypical by their large separation from nearby galaxies and high line widths. There is a hypothesis suggesting that they are dark matter halos containing gas, but little or no stars. So we took an extremely deep image of one of those objects with the Milankovitch telescope with the hope to detect a faint galaxy. The result is here, and as you can see, there is nothing. So this allowed us to estimate that the luminosity of the object has to be below 10 to the 7 of the solar, and that the object has to contain at least 3 times more mass and gas than in stars. So
1 minute left, sorry.
yes,
Okay,
I'm
okay.
just finishing. So here is my summary, and yes, so I think that this can be enough. Thanks for attention.
Thank you very much for a very interesting talk. So is there just one short question? You can, participants can just unmute themselves and ask a question.
Hello, Bilek. This is
Hi.
Anna. Very nice.
to hear
Can you hear me?
Just short, Anna, please.
Okay, just short. I was wondering just how deep are those CFHT images in the MATLAS survey? Do you know? I mean, I know you know.
you. Well,
No, for example.
yes, it depends. Well, it depends on it would be a very long question. So okay, so I will try for a fast answer. So the limit, the deepest images we have are 29 magnitudes per arc second square. But it obviously it depends on the photometric band. So we get the deepest images in the G band,
Yeah.
and we also have images in the R band, I band, and some of them in the U band. And these are, well, a bit worse.
Okay.
And
But was that 1 or 3 sigma limit? That's also important.
yes, yes, yes.
Yeah.
So the way surface brightness limit is measured in MATLAS is according to to the faint parts of galaxies or faint
Okay. Not
structures we
really.
see. So you just measure the surface brightness of the faintest structure you can detect by eye in the image, and this is called the surface brightness limit.
Okay.
As
Okay.
you know, there are many ways to measure the surface brightness limit, and none of them is accepted universally by everyone, and there is a big mess. And
Yeah.
so, well,
Sure.
that's it.
Okay. Thank you.
Thank you very much. Thank you, Michal, for a nice lecture once more, and thank you
Thank you.
for all participants. So we have to close this session, to finish this session. I thanks once more to all speakers in this session. And it is it. We really heard a lot of very interesting talks. Next extragalactic session will start in 11:50, and now it is we have small